electronics, I should say, and everything in between, then that magnetic field is going to similarly expand and contract in correspondence with the current that's flowing through the wire. And if you had another coil next to it, that magnetic flux that resulted from the current flowing through this wire is going to cross through this conductor. Go back to my last class. What did I say about magnetics and conductors? If you have a bar magnet here, north and south, it's got this magnetic field, and you have this conductor connected to some kind of meter, and you move it through the field one way, it will flip one way, and if you go back the way it came, it'll flip the opposite direction. A conductor crossing a magnetic line of force will generate a current flow. A current flow will generate a magnetic line of force. Very nice principle that a guy named Michael Faraday used to create something called the generator and the motor. But using Faraday's law, that integral of dphi dt that I talked about last week, which it simply means in calculus the rate that the flux changes with respect to time, is going to be equivalent to the voltage. And this negative sign is the Lenz's law principle that says you put a current in here, generates a magnetic line of force, or many, depending on how many coils you wrap around a coil form. And the flux, when it moves out, is going to do the exact opposite of the process that created it. Current creates magnetics, magnetics create current, the current that's created as a result of the expanding magnetic flux will produce a voltage opposite the one that created the flow in the first place. That's where the impedance of an inductor comes from. Alright, the fact still remains, if I put two coils of wire here, and I really should do it the other way around, because I want to make the voltage go down, not up. So I'm going to put lots of turns of wire here, and only a few here, basically 10 times as many here as I'm going to have here. The turns ratio is going to determine the voltage ratio. Remember, more turns, you get more magnetics. Fewer turns, less. So I'm going to create a magnetic field that's going to be created here and coupled into this guy. And if I have 10 times as many turns of wire around the core of this thing, and the core is a piece of soft iron. The reason we do that is it tends to be less impeding than air. And by doing that, it tends to pull all the magnetics into a tighter space, so it's a more efficient use. You find iron cores where you have power electronics, like 60 Hz cycles, in audio circuits, like, typically up to about 20,000 cycles per second, the audio range. When you get to the radio frequencies, they tend to use air because then the iron becomes too impeding. It basically doesn't allow the magnetic field to go through it quite as easily as air, so air is better than iron on a high frequency circuit like a radio frequency coil. And that's pretty much how you can tell one from the other. If it's an air core, it's typically an RF transformer or choke. If it's iron, it's for lower frequencies. And you don't have the problem keeping the magnetic field in a tight space. It's oscillating so fast that it doesn't move out that far. Anyway, if I have 120 volts coming in here and 10 times as many turns as I have coming out here, guess what I'm going to get? 1/10 as many volts coupled into this guy. So I've now stepped down. Transformers, which is this step here, change voltages. In a certain way they change current too. You got a certain amount of power coming in. So if the voltage goes down by a factor of 10, the amount of current you can draw goes up by a factor of 10. So if this is 1 amp on this side, that's 120 watts. And you'll get 120 watts here because this 12 volts can basically probably provide about 10 amps before it starts getting the metal here, make the voltage roll off a little bit. So that's the first step in the power supply. We have basically made the voltage that's too high into something that's just right, and it can be any voltage you want it to be. I just arbitrarily said 12 because a lot of stuff that's electronic tends to run around anywhere from 5 to 30 volts. It's pretty obvious when you have your USB device always plugging into almost anything that's got a USB connector. There's 5 volts there. And then again, if you have some kind of a more power-oriented circuit like an audio amplifier, those voltages tend to be close to the 30. They can be higher too, depends on just how much power you need. If you need a lot of power, you can either bring up the voltage or bring up the current. If you bring up the current, you're going to lose more in the copper. So if you don't have a lot of current that you have to draw, voltage doesn't have to be high. If you do, and they've been talking about this with cars, there's so many darn accessories in a car. You got about 30 electric motors that operate your windows and your wipers and your climate control system, the vents that operate heating and cooling in the car, and I can go on and on. That at 12 volts coming out of the battery, there's an awful lot of current being drawn. And there was a talk about tripling it to 42 volts, and you'd say, wait a minute, 3 times 12 is not 42, but the charging voltage is 14. They go a little higher voltage to get current to flow into the battery. And if they tripled that to 42, then they wouldn't need as much current flow. They could use less copper, et cetera, and it just died. Most people said that. Everybody owns a million accessories with a little cigarette lighter plug that runs at 12 volts. You're not going to obsolete everybody's stuff by doing that. They did it once back in the 50s when they went from 6 to 12 volts, and you know, we're not going to have that mission on Yiddish for craziness. However, guess what's coming down the line? Electric cars. So if the Tesla's there, hybrid cars are there. Those power systems tend to run anywhere from 330 to 480 volts. So higher voltages might show up, but they might show up as, you know, regular AC outlet when you plug things into your car. They haven't quite come up with an answer. It won't be that hard to provide multiple power supply systems for 12 volt accessories. All right, we've done the first step. We got the voltage down. Let's go to the next step. We want to convert AC into DC. How are you going to do that? Well, I'm going to introduce you to the first of many, or first of a few at least, so-called semiconductor devices that are good for that. Semiconductors aren't the only ones that do it. It used to be done with vacuum tubes. But this thing here is a diode. And it's like a one-way valve. The actual, let's see, if I is here and B is here. The actual charts look like that. Basically, if you get current, you don't get voltage, and if you get voltage, you don't get current. So, you know, it's either one or the other. What that means is, if you look at this triangle, which is sort of like an arrow, it's telling this conventionally the way the current flows, which means if the potential is higher on this side than this side, it will conduct, and you'll get current, and essentially almost no voltage. Be close to zero. If you go the other way, if you try to push current this way, you're going to get all voltage and no current. This thing, the voltage will be essentially, dependent on what voltage is applied, it'll be the same. It'll block the backflow. It's a one-way valve. You'll get all voltage, and essentially the current will, on the current axis, you'll be close to zero. So therefore, all I have to do is stick one of these guys in here, and if I start out with this, after I put it through this diode, what I'm going to get is something like this. Current will flow one way and it won't flow the other way. When it's in the negative half cycle, nothing flows. Okay, we solved the problem. But we did something we didn't want to do along the way. we're not gonna have 12 volts anymore because we threw away half of the power. I mean, half the time it's off, so the average voltage coming out of this thing's only gonna be 6 volts instead of 12. Oh dear, what do we do about that? Okay, how's this for an idea? Put 2 diodes in there, tap this thing somewhere in the middle of the windings, pull these 2 guys together. Now, half the time the cycle will go this way and be conducted here, and this will be your plus, and the return path will be here, and this will be your minus. Your life will be great. The other half of the cycle, meaning the negative half, it'll flow this way up to here, and the return path will be there. Solve the problem. Now we have what's called a full wave rectifier instead of what we had before, which was referred to as a half wave rectifier, where only half of the waveform made it through the diodes to the outside. However, I said I center tapped the windings here. So instead of getting 12 volts on, I got 6. But I got it at the same time. So basically I haven't really solved the problem. I'm back to getting half as much voltage as I wanted. Now I can solve that just by having a different turns ratio. Instead of 10 to 1, it might be 20 to 1 or 10 to 1 half. And basically what I'd do is I'd have 24 volts coming out of my secondary center tap, and each half of the winding would give me 12. That's one way to do it. That's very often the way it was done. But it was done in an old day when a rectifier didn't look like this, it looked like this. It's a vacuum tube with a cathode and an anode. And it was the same story. The current flowed that way. Now you're going to say, yeah, but the electrons, went from this cathode, which was heated up by this filament to a high temperature, about 600 to 800 degrees, so that you could boil the electrons off and get them to be captured by this positively charged thing called a plate, the target. Conventional current still flows from plus to minus. The electrons might go that way, but we conventionally say whichever way the positive carriers go, plus to minus convention. Not reality, just convention. Save us some math headaches. It's still going to be that way. But this worked the same way as this did. It's just that these were expensive. So using a center tap winding on a secondary was not a bad thing. Diodes are pretty cheap by comparison. So using more diodes doesn't seem to be a problem. So here's what we do. Instead of using 2 diodes, let's use 4 diodes. How's that going to look? It's going to look great. I'll show you how. Here's a node, here's a node, here's a node, and here's a node. And there's going to be a diode in each branch. So basically, where the AC comes in, you kind of have to get into the middle of the path. And means it's going to look like this. And finishing the job is going to be a case of be careful not to get myself twisted up here. I didn't get twisted, but I got a little bit sloppy in my artistry. Sort of like that. It's not right. One of these. AC should go in the middle of this thing. Oh yeah. I've got it. I have to stop and just kind of watch the current flow in my head. All right, it looks like that. The AC always goes between a cathode here and an anode there, and it's going between a cathode here and an anode here. So you got the alternating current coming in this way. And coming out this way, where the 2 pluses come together, you got plus. Where you got the 2 minuses together, you got minus. During half the cycle, the current is going to come on down here and flow out this way, And the return path is going to flow in like this and return that way. During the other half cycle, it's going to do the opposite. This will flow that way, and this will flow this way. You'll get a full wave, and you won't have to center tap the transformer. You can use a 12-volt transformer here, and when you're done, you'll have 12 volts DC here. It will be like this. But that's bouncing between 0 and some maximum voltage here in the positive sense. If you listen to that on your audio equipment, you will hear a 120 cycle hum. Now notice I didn't say 60 cycle hum, because now instead of the rep rate being 60 hertz, the rep rate is twice as fast, 120 hertz, because we flip the negative going part to positive, and the repetition rate is actually doubled. And you'll hear a pitch that's 120. So if you hear that hum in your amplifier, there's two good possible reasons for it. One is what's called a ground loop, which we'll get to down the line. And the other is you've got a bad filtering process. It's not taking the so-called ripple out of the converted DC that was once AC. So we're going to fix that. How are we going to fix that? With a filter. Do we have enough information to make a filter circuit? Oh yeah, we talked about all this stuff. Here's what we're going to use for a filter. We're going to charge up a capacitor. In fact, if we want to make it really fancy, we'll use a capacitor and an inductor. Remember, this thing likes to pass low frequencies and block high frequencies. This thing likes to pass high frequencies and block low frequencies. So all of the high frequency components tend to get shorted out here, and blocked here. And the low frequency components just go sailing right through.